techniques by which you can generate an AM signal. So how you are going to generate AM signal? Different types of AM signals are generated. For example, we have seen three types of modulation techniques of AM, that is double sideband full carrier, double sideband suppressed carrier, single sideband suppressed carrier, and distributed. All these generations were happened by means of a square law modulator, a balance modulator, by means of a nonlinear device like a diode or a transistor. And wherever we need a filter to suppress the carrier, we designed a filter. And of course, for single sideband, we gone for frequency discriminator and phase discriminator for generating a single sideband suppressed carrier signal. And also we saw the advantages as disadvantages of both the techniques of frequency discrimination as well as the phase discriminator. That is a modified frequency discriminator, which is going to be called as a phase discriminator, is going to have a better way of eliminating or suppressing the suppressed carrier instead of designing a very complicated filter circuit. Okay, so it's about your modulation sir. All these are the techniques used for generating AM signals. So that is at the transmitter. So at the receiver end, you are supposed to try those signals. Whatever may be the message signal which is getting transmitted by means of the carrier, you have to receive it and you have to remove the carrier from your message signal and retrieve the message signal. So that is the aim of the demodulation. Or demodulation is the process of retrieving the original signal from the modulated signal. Now you see how that is being done. So that is called as demodulation or detection. So demodulation can be done by means of linear detectors or non-linear detectors. So these are the two types of AM detectors, basically linear detectors and non-linear detectors. These non-linear detectors are sometimes called as square law detectors. And the linear detection has got two types. One is non-coherent or envelope detection. Another one is current or synchronous detection. So this coherent is going to be a linear detector, and in that you call it as a synchronous detector. What we have to do is get the modulated signal. So you receive the modulated signal. This modulated signal is multiplied with the carrier signal. Here this carrier signal is locally generated by means of an oscillator. See that the carrier signal is used at the receiver end is same as that of the carrier signal which is used at the transmitter end. It should have the same amplitude and the same frequency. That signal is multiplied by means of a product modulator with the AM modulated signal, and this product modulator is going to detect the envelope of the modulated signal, which gives you the V of t signal. That is going to be your transmitted signal, and this passing into a low pass filter will give you a resultant in a modulating signal. That is going to be the demodulated signal. This is the modulated signal we are going to receive. Pass it on to a product modulator that is going to be multiplied with the carrier signal which is locally generated. Then pass it on to the low pass filter so that it produces a modulating signal at the output. Okay, right? Now we'll see how this product modulator is going to do. So this is the principle. You are going to have a local oscillator which is capable of generating a carrier frequency, a proper phase and proper amplitude in order to retrieve the message signal from the modulated signal. And exactly it should be synchronized with the carrier in both the phase and the frequency. Whatever may be the phase or the frequency of the transmitted signal, the same should be used at the receiver end. Only then we call it as a synchronous detector. And here we have got a product modulator. This product modulator, what it does is, it is going to multiply the modulated signal with the carrier signal, which is locally generated. So this is going to be the modulated signal. Modulated signal comprises of Vm into Vc, carrier signal as well as the modulating signal. So this is the output signal. This is the input to the demodulated circuit. This is actually the output from the modulated circuit or from the AM generator. And this is the modulated signal. And this is going to be the carrier signal. In order to differentiate the carrier signal which was transmitted and the carrier signal which is being locally generated, you are going to represent the amplitude Vc and sine omega c, because omega c is going to be the carrier signal frequency. So this is the signal from the local oscillator. These two signals are multiplied by means of this product modulator. The product modulator has one input from the double cycle suppressed carrier voltage, that is Vm into Vc into sine omega mt into sine omega c. That is the incoming signal. And this is multiplied with the carrier signal. Okay, so this carrier signal is going to be represented as Vc dash sin omega ct. Multiply these two signals. The left hand side is modulated signal into the carrier signal. So that the V of t which is coming out of the product modulator is this Vm, Vc and Vc dash. All these three are the amplitudes of the signal. And of course sin omega ct and sin omega ct both together are going to be sin square omega ct and this sin omega n. So I'll make use of the trigonometric expression sin square theta. This one. Sorry, I had a call from faculty.
ஈஸ்வர் பிரசன் மேம் லேட்டா தான் ஜாயின் பண்ணேன்.
எப்போ யாருமா பேர் சொல்லு?
ஈஸ்வர் ஈஸ்வர் மேம்.
ஓகே
ஓகே மேம்.
Okay, ma'am. Now, let me have the mathematical expression for sin square theta is a minus cos 2 theta by 2. Just substitute in this place and you multiply the within the parentheses. So it will be sin omega into minus of this thing. And this signal is passed through a low pass filter. Low pass filter is going to be having all high frequencies like carrier term being removed. So it passes only the low frequency signal. So this carrier component is going to be a high frequency signal. All these high frequency signals is going to be get removed by the low pass filter. It passes only the emitting signal frequency, which is a low frequency signal. So output of the low pass filter is going to be having the amplitude factor as Vm, Vc, Vc dash festival into the modulating signal. Okay, so this is how we are going to demodulate and retrieve the information signal which was transmitted at the transmitter. And of course, why we call this as a coherent detector is you have to maintain the phase frequency of the carrier at the transmitter end as well as the receiver end as well. So this is single sideband, and next is the next type of demodulation. coordinator, all these topics.
Hello, ma'am.
Yes.
Ma'am.
Yes, Ajit.
Ma'am, Ajit present, ma'am.
Okay, ma. Please don't interrupt in between. At the end of the class, also I'll ask for attendance. You are joining late and asking for attendance. Does that make sense? Huh?
Ma'am.
It is your
Ma'am,
responsibility.
network problem.
That is okay. You have got network issue means wait for time. At the end of the class, you can ask for the attendance.
Sorry. Sorry, ma'am. Okay, ma'am.
Okay, now we'll see the generation under detection of your vestigial sideband. So already we have got the vestigial sideband. Vestigial sideband is going to have part of the upper sideband being suppressed because it is going to have low frequency component being suppressed. It is going to have a very small portion of the low frequency component and major portion of the high frequency component in it, so that it can process both the speech signal as well as the video signal. How you can do this is you should make use of a product modulator. As usual, it is going to produce a modulating signal and the carrier signal. This product modulator multiplies these two signals and it is capable of generating a double sideband of carrier. And this double sideband subcarrier is passed on to a band pass filter in such a way that it passes a band of frequency and it suppresses a portion of the frequency. The portion of the frequency which has to suppress should be depending upon the carrier voltage, carrier frequency FC and the vestigial frequency FB is chosen upon. Now, so this is how you are going to get a message signal and the carrier signal being multiplied, and you are going to pass it on through a baseband filter. Of course, the output of the product modulator has got the upper and the lower side frequencies, whereas the carrier is going to get suppressed, and vestige is going to have the transmission of the vestigial signal being multiplied. Now we'll see how we're going to demodulate or retrieve the VSB signal at the variant. So you are going to have the VSB signal being received, passed on to the product modulator. The product modulator input is going to be a locally generated carrier signal whose voltage is VC dash and omega C. This omega C should be the carrier frequency which was chosen at the transmitter end, and multiplied signal is referred as V of t. This signal is passed on through a low pass filter so that it removes all the low frequency component. It removes the high frequency component, passes all the low frequency. This is how we are going to see the vestigial sideband signal being multiplied with the carrier signal. Take Fourier transform of this is going to be represented in units of frequency domain. Vestigial voltage of the carrier component is subtracted from F1 and plus component is the upper band as well as the low frequency of the upper side band. And substituting the first equation, the second equation, so this is the first equation substituted over here and make simplifications about answer of the common terms. So we have got two terms result. One first term is going to be frequency spectrum of terminating signal, and the second is going to be the frequency spectrum of the residual sideband injected carrier. So after we ask this signal, the V of t, here it is given in frequency domain. Of course, you are taking the transform of the signal. So when you ask this V of t is passed through low pass filter. And part it, the second term is going to be the high frequency component is going to get removed or cancelled out, and you will be having the first term alone remaining, which is called the low. So this is how you generate your degenerate your vestigial. And now here comes a comparison of various reactions. And few characteristics of these signals are taken into account: the signal nature, bandwidth, power transmitted required, how power you are going to save, what is going to be the efficiency, what is going to be the modulation technique, level of opacity, detection technique, distortion level, and up. So of course, these four techniques are taken: modulation or generation of waves with full carrier, suppressed carrier, single sideband suppressed carrier in the studio side. So what is the nature of the system? Carrier is present, both the upper and the lower sideband is present in dual carrier methodology. The sideband only both the sidebands are present, carrier suppressed. Your carrier is suppressed, one of the sideband is also removed, meaning passing it through a filter circuit, only one of the sideband is removed. And here one sideband is there, in that also you are going to have a vestige part of available. Okay. So this is the signal nature of all these different AM signals. And of course, the bandwidth requirement is for both double sideband full carrier, suppressed carrier is going to be twice the modulating signal frequency. Whereas the bandwidth required may lie between either this 2 FM or this FM in case of your vestige sideband. In the single sideband, of course, only one sideband is present, so the bandwidth required is FM only. Coming to the power transmission, compare the total power needed is Cc into 1 plus Ma square by 2. Here you are going to have the carrier suppressed, so it is Cc into Ma square 2. Here it is Cc into Ma square by 4. Power required still reduces. And in vestigial, it once again it lies between both the suppressed carrier as well as the vestigial, a single sideband. We are going to have part of a single sideband. So you can always see that the bandwidth required lies between 2 FM and FM in this scenario. Power also lies between P of the state and P of single band and the double sideband. Less than that. That is the needed power. And how much power you are going to save? Of course, if you are going to not suppress the carrier means more power is based transmitting the carrier signal along with the sideband signals. So it is 33.33% of the power is going to be. Whereas coming to the double sideband suppressed carrier, it is 50%. And single sideband transmission has got enormous amount of power being saved, like 83.3%. And the last category, vestigial sideband transmission of AM signal saves 75%, not or 83%. It lies in. What is going to be the efficiency? Along with the carrier, it is going to be 33.3. Of course, this efficiency in these two categories comes to around 80 or nearly 100. Whereas efficiency of vestige lies between 100 and 33. Modulation technique, both these double sideband is going to be not much complex. It is going to be simple to construct. Whereas designing a circuit which is capable of suppressing one full sideband is going to be a complex methodology. And of course, designing a filter circuit which is going to remove only portion of the sideband power. It is going to be more complex when compared to this one. Okay, so modulation technique is going to be simple because it is scenario. And coming to the detection, the same thing of complexity occurs. It is simple to detect with the carrier, but without the carriers means you have to design the oscillator circuit, which is exactly what was used at the transmitter. Whereas here, along with the carrier, you are going to receive it. So you know what is the carrier frequency. So you can easily remove the carrier frequency, try the original signal from the envelope of your carrier signal. Whereas all these three categories are going to be complex because in all the three carrier is suppressed. So you should know what carrier frequency which was used at the transmitter end. Only then you can design a circuit which is capable of producing the same amount of carrier frequency, that too with the same phase. You have to generate and then retrieve the information signal from the transmitter. So it is much more complex than the first category of AM modulation. Coming to the distortion, the signal is get highly distorted when in your double sideband the full carrier, whereas a distortion is going to be somewhat lying between this and the single sideband. Okay, here it will be less in the last two carriers. Coming to the application, this one is used in AM broadcasting, whereas suppressed carrier is used in telephony, short distance communication. Single sideband with the suppressed carrier is used in wireless communication, especially in audio signal transmission. And of course, vestigial sideband we have seen it is used in the television broadcasting, which is going to have a combination of your speech signal and the video signal, where speech signal is going to be having high frequency components and the video signal has got low frequency components also present. So in order to have a combination of both, we go for a vestigial. Now, how your AM transmitter and receivers are doing? So, AM transmitter and receiver are classified into two low-level transmitter and high-level transmitter. This depends upon the frequency, okay, level of the power and the frequency. At low frequency or high frequency or at low power level, you are going to transmit or high. So, now this is the block diagram of your low-level transmitter. So here you are going to have the audio frequency signal and the corresponding amplifier for that, and a crystal oscillator is used which is capable of generating carriers at a radio frequency range that is more than 300 Hz to 300 kHz range. We are going to make use of the class A amplifier because both the signals are going to be not having sufficient signal strength in it, so we go for amplifier. This is put to a balanced modulator. This is going to be a information signal, this is going to be the carrier signal, and these are get amplified and set to the impedance matching system and transmit. This already discussed about each and every block in the previous question. Whereas the difference between low and a high frequency is here you make use of class C amplifier. So here for audio itself, make use of class A amplifier. In the previous case, you can go for any configuration. Like CV, mostly we prefer CV for getting high gain in case of the high frequency. So there is a difference between the low and the high. Comparison of these techniques. Modulated signal are further amplified after modulation to raise the power level. So at the output, before feeding it to the antenna, you have to once again amplify that. Whereas in the high level transmitter, message signal the carrier is sufficiently amplified before the modulation. So after modulation, sorry, no need to amplify the signal once again. Okay. And coming to the depth of modulation is less than 100% modulation depth. It is less than 100%. Whereas here it is going to have a modulation to be maximum 100%. But this modulation index will be 1. Whereas in this case it will be less than 1. And low level, of course, the name itself says it is going to deal with low power levels. So obviously the gain will be low and efficiency is also going to be low. Whereas here it is going to be high gain and high efficiency. And the application of this low level is going to be in the remote control, which is where we use our television, all other video game gadgets, all these things in use of low level. Power transmission is going to be less, where you need a battery power in it. So we design it like that, and in walkie-talkie, almost all these wireless devices. Whereas high frequency or high level transmitters, where the power level needed is going to be high because we have to transmit for a very long distance, we need high power level transmitter. So that's going to be used in radio and television signal transmission. Okay. Next we have to see the what is F1? We'll give the introduction to the FM and then we move on to the FM. So already we have what is FM? What is frequency modulation? What is frequency modulation?
Modulation and frequency level, ma'am.
Hmm? What you are going to do? Frequency modulation. How you get a frequency modulated signal? The very first class itself I designed the explanation for it. What is it? Varying the frequency of the carrier signal in accordance with the message signal. That is going to be the modulation. Am I right? Okay. Is this visible? So in the first unit, we have seen the different methodology of the analog modulation schemes as well as demodulation. The AM signal was generated. We have seen the characteristics, power calculation, efficiency calculation for all modulation schemes. And also we have seen the modulator as well as the demodulator. And the part of this unit is going to be the angle modulation. There are two types of angle modulation. One is phase modulation, another one is the frequency modulation. Here also we are going to see the various representation of the signals and as well as the power spectral density of the PM and the FM signal, and how to modulate and demodulate the frequency and the phase modulated signal, and of course the application of the FM signal where we are going to see how the super heterodyne receiver works. So angle modulation, we are going to be classified into frequency modulation and phase modulation. So what we are going to see is the modulation, demodulation of it, and the power spectral density. Similarly, phase modulation. So this is the outline of this topic. So already we have seen what we are going to do with the signal. It has got three parameters: amplitude, frequency, and phase. With respect to the modulating signal, we are going to vary the amplitude carrier. It results in AM. We are going to vary the carrier frequency with respect to the message signal. It results in FM. And we are going to vary the phase of the carrier signal with respect to the information, then it results in C. So of course, this FM and PM are closely related and grouped together as phase modulation, or work together is going to be the angle modulation. So this type of modulation, the frequency or the phase of the carrier is varied in proportion to the amplitude of the modulating signal is called as angle modulating signal. You can see the variation over here. When you observe the variation, the carrier frequency is going to get varied. Here you can see the signal has got very high frequency, whereas the signal is going to be low. So this variation depends upon the information signal. Of course, here it is shown. So this is going to modulating signal. This blue color sinusoidal signal. The red is going to be the high frequency signal. And this is AM modulated signal, which is going to be a blue color part, where it is going to be having the envelope modulating signal. And this is the frequency modulation, where there is a variation of frequency of the carrier region. Here the carrier signal has got uniform frequency, whereas it has got varying. Can be depicted like this. Amplitude varies, frequency varies, time section between T1 time period, T2 time period, T3 time period. Frequency varies. There is a phase node phi 1. With respect to this, the change in the next signal, phase, and the another signal. So this is in time domain. You can see how the signal is behaving. And coming to the modulation index of the angle modulated signal, in case of AM, it is Vm by Vc, amplitude of the modulating one divided by amplitude of the carrier signal. Here, the shift is proportional to the instantaneous amplitude of the modulating signal, and according to that, you can have the coefficient denoted as Kp, which is equal to phi by Em. So the phase modulation, we are going to change the phase angle of the signal, where the phase angle of the signal is going to be the carrier signal phase angle is varied in accordance with modulating index value. Okay, and your M of P, that is a message fix. And here, of course, omega C is equal to 5. Coming to the frequency modulation, it is omega C plus Kf of M of P. This Kf and Kp. Here Kp refers the modulation index of the phase modulated signal. This refers to the modulation index of the frequency modulation. A. Where this theta is going to be integral 0 to t omega I of t into d. The substance integrated will be having the expression. Okay. I think I can wind up the class with this topic today. Good morning. We will continue later. Okay, thank you for this. I have given attendance for the date from now. Thanks.